This is a lecture on a MOSFET. MOSFET stands for Metal Oxide Semiconductor Field Effect Transistor. And in this course, we focus on the enhancement mode N-channel MOSFET. We'll also briefly talk about the enhancement mode P-channel, because very much like once you understand an NPN BJT, with just the added knowledge that you flip the voltage sources in order to operate a PNP. Same sort of thing with N-channel and P-channel enhancement mode MOSFETs, that once you understand an N-channel, you'll see that just by flipping the polarity of a couple of sources, the P-channels work in the same fashion as the N-channels. Now there's also depletion mode MOSFETs that I'm not going to talk about in any of my videos, but it is covered in our textbook. And once you understand one type of MOSFET, I think it's pretty easy to understand the other type. So first we're going to look at or talk about just some basics of MOSFETs, and also look at the operation when the voltage VGS, which is the gate to source voltage, is equal to 0 volts. And in order to do that, let me just bring over this slide here. And what this shows is that, well, first over here, this is the circuit symbol for an enhancement mode N-channel. This arrow here pointing in indicates that it's N-channel. If you have a P-channel, this arrow points out. But there's 3 connections on a MOSFET, just like there's 3 connections on a BJT. But the names of these leads, these connections, are different. Remember, with the BJT, you have emitter base collector. With FETs, you have a source lead, that's the S, a gate lead, that's the G, and a drain lead, that's the D. So this is just the circuit symbol for the enhancement mode P-channel MOSFET. And then this is how the enhancement mode P-channel, or excuse me, this is N-channel, excuse me. This is N-channel MOSFET, again, the arrow pointing in. And this is the fabrication of an N-channel enhancement mode MOSFET. And you can see that there's 2 N regions separated by a P, which is called the substrate. And the plus signs next to the N's, that doesn't indicate positive charge, because as we know, N-doped semiconductor has electrons as its free charges. What the plus indicates here is heavily doped. So each one of these corners, one by the source lead and one by the drain lead, there's lots and lots of free electrons that are just waiting to contribute to a current. And then in between the source and drain, that's where you have your gate. So when VGS is equal to 0, as we have here, where there's no source connected up to the gate lead, there is no channel, there is no connection between the source and the drain. See, these 2 N regions are separated by this P. In order for there to be a channel, you have to have a continuous medium of N here to make an N channel. So there would have to be a connection between these 2 corners of N-type material in order to have a conductive medium, a channel between the 2 ends of the MOSFET. So in this case, where there's no channel, the resistance of the channel would be ideally infinity. So between the source and drain, when VGS is equal to 0 for an enhancement mode MOSFET, it acts like an open. Okay, there's essentially infinite ohms here, ideally, so it's like a switch that's off. Now, if we go back to my notes, okay, well, if we put a positive voltage on the gate, what happens is that creates an attractive force for these free electrons that are in the corners. So those free electrons migrate towards that positive charge on the gate. And at some point, you'll just get a connection. You'll just get a continuous medium here of N-doped semiconductor between where the source and the drain is. And the VGS voltage that occurs, where you just get this narrow channel of N material, is called the threshold voltage. So at this point where VGS equals the threshold voltage, you now have a channel okay, because the channel just developed. Okay, so channel just develops. Okay, so you see here the resistance of the channel, equaled an open, okay, because there is no connection at all between the source and the drain. But here, where the channel just develops, you have an R channel, but it's equal to a high amount of ohms. It might be millions of ohms. Okay, but at least now you have a connection, where before, when VGS was equal to 0, there was no channel at all, and there was no connection between the source and the drain. Okay, so the VGS where this just occurs, that's called the threshold voltage. Well, now if I continue to increase my gate voltage, okay, I make it more positive, okay, then this is what occurs, is that as I make the gate more positive and more free electrons are attracted in between the two corners here, well, the width of my channel, the cross section of my channel, increases. And as the cross section of the channel increases, the resistance of the channel decreases. Okay, so as I put more positive voltage on the gate, I'm getting a wider channel and therefore less resistance in the channel. Now you can see that the channel is not totally symmetric, that it's wider on the source end than what it is on the drain end. And that's because since the source is grounded and I have this VDD voltage here, which for this discussion is a couple of volts or so, well, there's a bigger positive difference between the gate and source than between the gate and drain. So that's why you see a wider channel end on this side. Okay, so the key point is, though, as the gate voltage is getting more and more positive, the channel is getting wider and the resistance of the channel is decreasing. Okay, so here you're going to see that our channel, right, is getting smaller, and at some point when VGS is much greater than V threshold, you're ideally going to have a short, that your channel is going to have a minimal amount of ohms. Ideally, a couple of ohms or so, but ideally we just say at that point it acts like a short, so that's a switch that's on. So I think you can see in this discussion that these FETs, just like BJTs, can be used as switches, since when VGS is equal to 0, it acts like a switch that's off, and when VGS is much greater than the threshold voltage, it acts like a switch that's on. Now, just to give you some indication what we mean here by much greater than, threshold voltages for a lot of different FETs are around a volt or so, some a little less than that, some a little more than that. But, if your VGS was, say, 5 volts, that would be considered much greater than in a lot of cases. Okay? Now, just real quickly, if you have a P-channel enhancement mode MOSFET, the only difference is you switch the polarity of the sources and the operation is the same. Okay, so switch polarity of both your gate voltage and your drain voltage. And that's because when you have a P channel, well, it's just the opposite fabrication, that instead of a P substrate, you would have an N substrate, and then these corners would be highly doped P regions. So you would need a negative voltage on your gate and also a negative voltage here on your drain, so that you would create a channel as the gate voltage was more and more negative. So it's the same discussion as with the N channel for the P channel, just the polarity of the sources are switched. Now, also, let's look at the IV characteristics of an enhancement mode MOSFET. Okay, so this is the IV characteristic of an enhancement mode MOSFET N channel, showing drain current versus drain to source voltage. Okay, so this is just like for the BJT when we had collector current versus collector to emitter voltage. And a big difference though is that with FETs, these curves here are constant voltage curves, okay, constant VGS curves, where with the BJTs, these were constant base currents, if you might recall. So here's a fundamental difference between BJTs and FETs. BJTs, as we discussed before, are current control devices. Okay, we're controlling a collector current with a base current. FETs, like a MOSFET, they're voltage control devices that we're controlling a current through a channel, okay, which is what your drain current is, with a voltage that's across the gate to source. Okay, so this gate to source voltage is determining the resistance of the channel, which thereby determines how much current is flowing through the channel. Okay, notice here that there's no curves below the threshold voltage of 2 volts, and that's because, remember, right at the threshold, that's when you just develop a channel, so that's when you would just have a current, you know, flowing through your channel. Anything below, any VGS below the threshold voltage, the channel isn't open, so no current's going to flow. So that's why you don't see a curve here. Okay. So also the shape of these curves, where you have this flat portion where VDS is more than a couple of volts, and then they drop off if VDS is less than a couple of volts. Well, this is the same type of curve with the BJTs, and you might recall that in the portion of the curves where the curves are flat, you have optimum gain, and that's where you operate the BJT as an amplifier. Well, same thing here with FETs. FETs can be used as amplifiers as well as switches. And in this course, we don't go into the analysis of an FET amplifier, just mainly due to time. You know, we do cover the BJT amplifier analysis as you saw earlier in the course, and we do cover both transistors being used as switches. Okay, but if you're interested in an FET amplifier, there is a discussion in our textbook. But again, just for time purposes, we're not going to spend any time on FET amplifiers. Now, you may also recall with the BJTs, we had an IV curve between the base current and the base to emitter voltage, and that was the same as a forward bias actual diode. Well, with FETs, we don't talk about an IV curve at the gate side, and that has to do with the fabrication. Okay, if we go back to this first slide here, okay, not shown on this slide, okay, but very important. In the fabrication of a MOSFET, they always put silicon oxide, okay, the silicon oxide material between the gate contact and the body of the MOSFET. And the key aspect of the silicon oxide is that it has very high impedance. So what this means is that for typical values of voltages at your gate, which are typically single-digit voltages, you know, usually not much more than 5 volts, and of course it can be as low as 0 volts. Well, for typical values of gate voltage, because this silicon oxide gives such a high impedance, the amount of current that you have at the gate is, in most applications, negligible. Okay, that you can just basically ignore it and call it 0. And in this class, that's what we're going to do. We're not going to worry about what the gate current is. We're just going to say that for all practical purposes, for the values of voltages that we're using at the gate, that our gate current is just 0. Okay, so that was our general discussion here on FETs. The next video we'll look at using a MOSFET as a switch in a circuit.